What we're doing here is the fundamental science of how complex, fully functioning, living ecosystems actually come together. Most of my professional scientific life I've spent studying what you might call fully assembled ecosystems with communities that are complex and interacting. A lot of it studying tropical forests in the Amazon basin. A lot of it studying thawing permafrost in the Arctic, which look much simpler than a tropical forest, but in reality have all kinds of complex microbial functions that interact biochemically with the plants there and create greenhouse gases like methane. When I was asked a few years ago to be the science director of the Landscape Evolution Observatory, I saw it as a great opportunity to look at the things from a completely different perspective. It's really been a transformation from when I first started learning about climate change in graduate school, when it was something that I think scientists talked about as a problem that we were facing for the future. And it's no longer a problem of the future, it's a problem of today. The world is changing and it's not the same Earth that we first studied. I think everybody is now feeling the effects of global climate change in their own life. Here in Tucson, Arizona, where I've lived now for 20 years, it's just evident now that just in the last 10 years, we spend more days above 110 degrees Fahrenheit than we did when I first moved here. When my daughter was a little girl, there was time for her to play outside that has shrunk. And so I think everybody is seeing that manifestation of that in different places, depending on where they live, whether it's, the risk of fires in fire-prone areas, whether it's along the coast, the risk of tropical storms and hurricanes that has increased the threat to those locations. Politically, it's a big problem. Technically, it's not that hard to stop. To put it as simple as possible, stop burning stuff, whether that's fossil fuels in the form of coal or oil, or whether that's tropical forests that are being burned down in order to make way for agricultural uses of the same land. Scientifically, we still need to understand the way that the Earth system as a whole will respond to climate change. And so we set up this magnificent laboratory here at Biosphere 2, the Landscape Evolution Observatory, not so much to help solve the climate change problem, which is a human political problem, but in order to understand the Earth system and how it will respond to climate change, how we fix damaged and degraded ecosystems. What we're doing here is the fundamental science of how complex, fully functioning, living ecosystems actually come together and work. We're building an ecosystem from the ground up, and you only really learn how something works when you have to build it from scratch. And that's what we're doing, is learning how to build a complex, fully functioning, increasing diversity system from scratch. We've started from basically 500 metric tons of ground basalt rock, and that's all there was to begin with. And now there's increasing complexity of microbial communities. There's cyanobacteria photosynthetic crusts that have colonized parts of the land surface. Once those get established, early successional mosses have come in, creating this green carpet across these landscapes. So we've now already come to a place just 10 years later that is completely different from sterile crushed rock, and we're about to launch to the next phase of putting vascular plants with complex root architectures that will act as straws, suctioning water out of this system and pumping carbon into it through photosynthesis from the carbon dioxide in the atmosphere. We'll watch and we'll create this fascinating fully functional ecosystem and see how it interacts with the water cycling through the system, the way it interacts with the carbon dioxide in the atmosphere. And it will be a new insight into how Earth systems interact with climate, how we can restore degraded landscapes here on Earth, from the first principles perspective of how life interacts with a physical system and comes together to create a multifunction ecosystem that has complexities that you couldn't have predicted from either the physics or the biology alone.
In the field, they can do similar measurements using a flux chamber to get carbon and water flux. But in the field, we can't control when it rains. So if we want to look at differences in how long it's been since the last time it rained, and we want to get one the day after, and one 3 days after, and one 10 days after, if it rains again 3 days after the first rain, we're out of luck. We have to start the whole series of measurements again. Whereas in Leo, we can control the rainfall, we can control magnitude of the rainfall, and then we also have all these sensors embedded in the slope that allowed us to get a lot more extra data that we simply wouldn't be able to measure at that scale in the field.
We've gotten funding from the National Science Foundation. We've gotten funding from private foundations, which are interested in sort of helping understand how we can better sustain and support the Earth system. One of our biggest challenges is just deciding what actual thing to do among the many options that are there. We only have 3 large hill slopes. It's a replication of 3 at most, so we can't do every manipulation that you might think of, whether it's we want to understand the effects of warming on this process, we want to understand the effects of droughts, we want to understand the effects of elevated CO2, carbon dioxide in the atmosphere, which is what's causing climate change. All those things are happening. They're affecting plants, they're affecting how plants and microbes interact. So we have to sort of be careful and choose among the many options to choose the things that we think are most important for learning the next step of how the ecosystem gets more and more complex as it evolves, and understand that complexity, being able to model and understand and predict that complexity, to be able to predict what happens if we perturb the system with something unexpected like a drought or a flood or extra CO2. All those things go into sort of figuring out how the system works.
This involved really a lot of physical work. We would go up in this gantry crane basket, almost like a window washer uses, and we would take measurements using a little flux chamber that we'd put down on the hill slope at a bunch of different points. And so we got to take advantage of all the sensors and controls that LEO has to measure carbon dioxide and water vapor flux at the critical zone. We were looking at how water and carbon are moving out and in based on different kind of plant growth on them. We had to take our measurements at different times of day to find out how the flux would change. And so we would go out there at 9 o'clock and be there till midnight or later, taking all these measurements. Since LEO is a controlled environment, the original flags that we put down to mark the hill slope were not stainless steel. They were like lawn marker flags that had iron in them. And so we realized these are not a sustainable thing to leave in the hill slope, because they're going to start leaching metals into the hill slope and compromise some of the metal concentrations, which are very low. And so we had this kind of rush about 2 weeks in after we put these flags down to change them all out for a better sealed one.
I'm a professor also, so I teach classes, but a lot of times are spent in meetings, writing proposals for funding the experiments that we want to do on LEO. That's a big part of being a researcher, is persuading colleagues that the idea that you have is an important one that should be funded. So that's both talking to people, having meetings, writing papers, writing proposals. Some fraction of my time is here at Biosphere 2, working with the staff here. We have a magnificent staff that is making all this happen. Working with colleagues who are coming here to do experiment, working with students who are learning and training how to be scientists on the Landscape Evolution Observatory, making measurements of the fluxes of CO2, the fluxes of water vapor, watching how water percolates through the hill slopes. All those things are done by a fantastic group of staff and scientists and students.
They taught me a lot about how much work in research, especially in a lab that's so big, is maintenance, and just making sure that you consider all of the things that go into a controlled experiment. It gave me a lot more to think about pursuing research as a career, because I had kind of gone into college with this broader ambition to learn more about science and to eventually work in environmental science. And I think working at LEO sort of showed me that I really like the experimental design end and figuring out everything that goes into building an experiment. But I really like even more implementing the experiment and having to problem solve in the moment, like with those lawn flags.
It may even give us insight into the complexities of terraforming Mars or other planets. It's basically, the fundamental science of how life creates ecosystems. You might be able to terraform Mars to be livable, or you might terraform the Earth or to restore it. But one of the things that we really wanted to focus on was the fact that terraformation happens not at the planetary scale all at once, but happens at the scale of landscapes. It happens at the scale of individual and communities of plants operate on and transform the soil, build the soil from the ground up, change the chemical composition of the soil, change the way water moves through the landscape as a whole. And at its foundation, terraformation is landscape terraformation. And even when you get to the planetary scale, it's an aggregation of this mosaic of landscapes. And so that's what we decided would be the best way to name the science that we were doing. Not only name the science that we were doing, but create the infrastructure or the disciplinary mindset for how we needed to understand the system, which was the blending of biology and physics and chemistry and hydrology and geochemistry into making how a landscape functions at the scale that you see at LEO. LEO is sort of like the smallest unit of a landscape that you could imagine that is across the whole Earth's surface, ultimately. And so therefore, if we want to understand the whole Earth behavior, we need to understand it as landscapes. if we don't know for sure that we can terraform Mars, we better not trash this one too badly before we sort of put our chips on that risky option.